So I'm just doing a little blast from the past tour of my StackExchange in physics, and the StackExchange website's gone weird for some reason recently. It's all back to basic text, but yeah, this is something I posted back in 2018. It's basically what I posted before. I was I'm just baiting the people on here more like I think. As could the gravitational field be a cloud of particles, not curved space time? Um, and there was some saying generally, oh no, absolutely not, it couldn't be. And I was gonna be all clever and try to trip them up by saying, well, if a gravitational field is not a cloud of particles, how can you have quantum gravity then? There's no quantum of gravity. If the gravitational field isn't particle based, or its basis isn't, a multitude of a single particle, how could it be quantizable? Do you see what I mean? So just going through, yeah, what I said originally. I was thinking more of particles from the object tunneling to within what we refer to as the gravitational field of the object rather than free particles floating around in space, which this first fucking dickhead completely dismisses and overrules, or doesn't pay heed to. I have this idea that the graviton is the electron. If this were true, it could clearly account for gravity quantitatively, as the number of electrons in an object is proportional to mass. My idea, well, the idea is taken on a slightly different dimension. I think since then, I've now added in W plus and minus bosons to directly mediate the force between electrons and protons. I'll get to that in a minute. Alright, so B. Ross theoretic gravitons are definitely not electrons. Electrons have charge, mass, and spin half. From analysis of gravitational waves, the upper bound on the mass of the graviton is 29 orders of magnitude smaller than the rest mass of an electron, not to mention charge and spin. Yeah, he's actually got sort of a point there. I mean, the idea I eventually developed, I suppose the added subtlety or the additional bit of sophistication within the model, if you like. This idea that it's, in the first instance, transmitted over large distances, yes, by tunneling electrons. However, there's an intermediary exchange of bosons, force-carrying particles, from the electron that is tunneled to the proton that it's tunneling to. Right? So, that might be a little bit hard to, wrap your head around. But, yeah, so any interaction between any two fermions in nature, any two matter particles, is always mediated by a boson. So if two electrons come within a close enough range of one another, that one electron will spit out a photon at the other electron, and it will be repelled, and that's how the negative charge of the electron manifests. Then if you have one W particle minus and a W plus particle being exchanged simultaneously, you drag two particles together, right? So you'd be dragging together an electron and a proton, or any other positively charged bundle of quarks. Yeah, so a W particle and a minus particle both have mass. They have a spin 1 each, and they have a certain mass, and they have obviously a spin of a charge of positive 1 and negative 1. So if you put those two together close enough, they attract one another, but they're also attracted to the electron and the proton in the same area, right? Which is where they end up. But their mass reduces to 0 because the opposite sign charges attract one another, and gravitation is mostly caused by charged particles, or the effects of charged particles on a macroscopic scale. So we're in this super particles and the super fermions. All these fermions, almost all of them, have, well, there's neutrinos as well, but those don't have charge. We can discount those for the time being. All these particles are charged, like all the particles in my face, body, clothes, etc. They're all atoms, all electrons. The outer shells of those atoms, and then there's the air around it, which again is made of atoms and hence electrons, and the electrons are just repelling one another constantly. Likewise, also, planets such as have a kind of haze of electron around them. So they're, just left over from all the atoms that make up the planet, right? Likewise, all the protons and all the atoms in the atmosphere and so on, these are constantly exchanging W particles with the electrons in the background, if you see what I mean. Keeping the air, for instance, close to the surface of the planet and not out in space. So there's greater force of gravity when it's closer to the planet, because the closer you get to the surface of the planet, there are more electrons towards the surface. There's a greater force of gravity pulling objects down. God, where was I? Tired. So I was just finessing that idea a bit. But the electron is very crucial in transmitting this force of gravity. One thing, it does create a massless spin-2 gauge field, but in this intermediary stage of transmitting the W particle between the electron and the proton, and it all as a kind of a maelstrom of particles that cause these two larger particles to move closer to one another. In the exchange, a sort of a slingshot effect, if you like, around in the exchange of the W plus and minus. And the mass in that massless spin-2 field, this composite field of two particles, the mass in there reduces to zero, because our masses, this is what I was getting at, are determined by our resistance to acceleration in gravitational fields. So the greater the extent to which we feel the pull downwards of gravity, there's resistance to acceleration. There's something keeping us on the ground, preventing us from moving forward and faster. So if I chuck this across the room, it's not going to carry on unimpeded until the end of the universe, is it? It's going to fall somewhere in the middle of my living room floor. So all the atoms in this, for one thing, that they're being buffeted by electrons. The electrons are being buffeted by electrons in the atmosphere, and this buffeting effect, that also increases as it gets closer to the ground. But likewise, the attractive force from the protons also increases. So, the aggregated effect of this, and the reason why there's not just an equal and opposite cancelling out of there sort of is. That's the other thing. Because it's getting buffeted, and because it's been given an initial kick of kinetic energy from my hands, and because it is feeling this tug of gravity downwards, it starts out with some force, a finite amount of force, but because that energy has been converted into momentum, it eventually will cancel out. Because it's encountering resistance. If there's no electrons buffeting it, just carry on forever. Now, because it's being pulled towards the ground, it encounters more and more electrons, gets slower and slower and slower. it hits the ground. It hits the ground and finally encounters too many electrons to penetrate, or buff it to the side as what happens in its passage through air, and it hits the ground. Yes? So, there we go. Physics. I think that's true. That's hard to dispute, I think. I was very likely. What's the rest of his comment? It's always good to be thinking and curious about the world, but in order to advance our understanding of quantum gravity, a theory on the cutting edge of physics, to lead to the best and most knowledgeable minds of the past century, you'll need to master a good chunk of known physics first. Cheers. Okay. Yeah, it did help. I mean, actually, his comment, did help, in fairness to it. Like, yeah, that's not one of the, shitty ones I was going to take the piss out of, I'm sure, Also, the number of electrons in an object is not proportional to mass. I'm sorry to say, it is proportional to mass, unfortunately. The proton has no electrons, yet it is massive. Oh, good God. What are protons almost always surrounded by in nature? Alright, okay. I know there's cosmic ray protons, yeah, but I mean, there are also cosmic ray electrons, and I'm not saying nucleosynthesis happens, but I mean they'll be buffeting into stuff, and there'll be free electrons for a bit, then they'll be transferred into some atom or molecule, or some chemical exchange or whatever. But yeah, okay, in most cases, in planets and so on a planet and so on, where you encounter protons, essential atoms which have electrons surrounding the nucleus. Man, come on. You know better than that. Your comment, first of all, was quite good. Proton has no electrons yet as matters. Consider neutron stars, different isotopes of atoms, ions, etc. Neutron stars are fascinating. Yeah, definitely. I mean, they've got, a proton at their core. Quark gluon plasma, that is a proton. And yeah, they got neutron around the proton, I guess, because neutrons are slightly lighter than protons, I think, aren't they? But what that means is they're less resistive to gravity. So, the inward crunch of proton, up quark, mostly. It was down quark, lattice outer layer with free electrons travelling around in between. And then you've got the gravitoelectric field, or the gravitoelectric weak field, if you like. What is basically a big atom. And we can have some free electrons in the lattice of the neutron star. I think most of the electrons, if you like, they're just the gravitational field. It is. If we look at black holes, I know this must be going on with black holes because we can almost actually see it. See, a hazy disk, it's an electron density. It's just what the bit we can't see is the nucleus, right? And much is actually the same. Much the truth is actually the same of neutron stars. Well, we can see the nucleus, and it emits light, and that is what would be the nucleus. But I mean, pulsars we can't. Not really. They're shooting out too much radiation. Yeah, it's converting all that to radiation. We can't so much as such see the nucleus. You can't see the surface of a pulsar, I don't think, can you? Quite. But yeah, neutron stars can see the surface. So that is the nucleus, if you like. Yeah, gravitational fields. Black holes, event horizons, or a supermassive black hole at the centre of the galaxy is think there's as a cloud of electrons. That is what that is, I'm certain of it. I'll eat my head if I'm wrong. I will, I'll eat my head. I'll do my best to do that.